to my talk. My name is Konstantina Christakopoulou. I'm a PhD student in the University of Minnesota, and I'm going to be talking to you about interactive learning for recommendation. So let me share my screen with you. Okay, so this presentation is going to be based on joint work with my advisor, Professor Arindam Banerjee, and also Philip Redlinsky and Katja Hoffman, who are in Microsoft Research in Cambridge, UK, where I did an internship last summer. So the outline of this talk is the following. First, I'm going to give you some motivation for why recommenders, why interactive learning, and why we should bridge the gap between the two. Then I'm going to give you this use case for interactive learning for recommendation, and it is going to be conversational recommenders for restaurant recommendation. And finally, I'm going to give you a very short glimpse into another work called collaborative ranking with a push at the top. Okay, let's start with the motivation. So the motivation for recommendation is the following. We live in this era of information overload, where every day there are these millions of new news articles, new tweets, and generally content being generated. So there is this need of having recommendation systems which are trying to deliver the right content at the right time to the right users. So if you look around the industry, you can see that, for example, in Netflix, you get personalized recommendations for movies. Or in YouTube, you get personalized recommendations for what videos you want to watch. Or for example, in Amazon, you get recommendations for what you should buy. Or you get Google News or Yahoo News, your personalized newsfeed. Or Pandora and Spotify, you get your personalized radio playlist and so on. The list goes on and on. So the main point here is that recommender systems are all around us and they're helping us in our everyday lives. So recommender systems actually got this big boom around 2006, where there was the Netflix prize, where essentially Netflix released this large data set of how different users have rated different movies in terms of ratings of form 1, 2, 3, 4, 5 stars. And the goal of this Netflix challenge was that the different researchers and industry people were supposed to beat the baseline that the Netflix had so far in order to be able to predict with how many stars the users are going to rate the different movies. And the goal was to beat this baseline that they had in terms of the root mean square error. So, however, this whole challenge focused on offline recommendation, meaning that somehow this dataset of users and movies was given to you in this offline dataset, and you were supposed to do well just on this offline dataset. However, in reality, we have this need for online recommenders. And the reason is that if you're trying to deploy, an offline recommender in some online system, there are a number of disadvantages which are linked to that. So one is that there is certain cost of trying to retrain the model. Second is that there is some potential mismatch between the offline and the online behavior, meaning that even if you have just managed to create this perfect model for your offline dataset, this might not do well in some sense of an online metric. And finally, there is also the failure of trying to capture the preference drifts that the users might have, exactly because this was offline recommender. So take as an example, the example of news recommendation. I'm going to give you now the overview of what recommendation as an interactive process would look for such an application. So essentially, the idea for interactive recommenders is that there are two components where the interaction happens. There is a component of the model, and then there is a component of the user, and the two interact with each other. So that's a huge difference among interactive recommenders and offline recommenders, because offline recommenders assume that there is this data set given to you somehow, whereas if you're trying to model recommendation as an interactive process, you actually assume that there is a model which actively to show to the user, and there is a user which is giving feedback to whatever the model gives to him. So to be more concrete, what is happening is that, let's say for news recommendation, given the context, where the context could be a user in terms of his explicit features like gender, age, past interaction history, past browsing history, and so on, or some other latent features, and also given this available inventory per day, which could be the curated news per day, the model decides what to show to the user. And then the user gives feedback on whatever news article the model showed to him. And this feedback could be explicit in the form of a rating or in the form of thumbs up, thumbs down, or it can be implicit, let's say click or skip or dwell time, meaning how much reading time on the news article and so on. Then the model gets this feedback and gets updated. And then using these updated parameters, it decides what to show to the user next. And the user gives feedback and so on. And this whole procedure continues. And the goal of the model is to actually maximize some average cumulative reward, which could be measured in the form of some metric like click-through rate, reading time, and so on. So now that I have described to you what this interactive learning for recommendation looks like, I'm going to go into more detail about what are the key pieces which are needed for that. So the first is what kind of model do we use for interactive learning for recommendation, so for the recommendation part. And on this talk, I'm going to focus only on collaborative filtering. And the second piece is how are you going to do the interactive learning? And the way we're going to do that is via bandits. Okay, so for the first part, which is what is the model for recommendation, I'm going to be talking about the latent factor model. So latent factor model is a subcategory of collaborative filtering. So generally speaking, collaborative filtering is this idea that similar users, they tend to rate different items similarly. And there are two large threads of work in collaborative filtering. The one is neighborhood-based models, and the other is latent factor models. So for this talk, I'm only going to talk about latent factor models. And actually, latent factor model is a very powerful model which is being used widely in industry. And this actually was the key piece in the winning solution for the Netflix challenge. So what the latent factor model tells us is that, first of all, assume that you have this data set of users and items, and the different users have rated either positively or negatively the different items in terms of explicit or implicit feedback, like click or no click, or like or dislike. So then given this data set, what the latent factor model does, it tries to explain the ratings of the different users on the different items using the following variables. So the one is that every user I is represented with a variable of alpha I, which is the user bias. And this tells us how likely the user is to like all possible items, like how likely he is to give high ratings to the items. And also he's represented by this d-dimensional vector, which is the vector of the user trait. So this captures the latent attributes of this user. Now, similarly, every item j is represented by a variable beta j, which is the item bias. And so this captures the popularity of this item. And also it's represented by the latent trait, which is the vj, which is again some vector in the same low dimensional space, d-dimensional. So essentially the idea here is that both the users and the items, they are projected in the same low dimensional space. And so this allows us to be able to capture the similarity between the different users and different items by taking the inner product of these two traits. So now, for those of you who are aware with the graphical model representation, this is what this model looks like. Actually, an alternative name for this model is probabilistic mass factorization. And so what you can see is that it's again the same variable that I talked to you about in the previous slide, but what you can see is that every variable comes from some Gaussian distribution with a certain mean and a certain variance. And then what this model does is that it models the noisy affinity of user I and item j, meaning how likely user I is to like item j, as the sum of the following terms: the term of the bias of the user, the bias of the item, and the inner product between the latent trait of the user and the latent trait of the item. And now, exactly because we have ratings of the form 0 or 1, like or dislike, we're thresholding this noisy affinity with 0 in order to have what is the observed rating. So this is what the model, the latent factor model looks like. Now, let's look at what is the second key piece that is needed for interactive learning for recommendation. So how are we going to do actually the interactive learning part? And the way we're going to do that just in this talk is going to be bandits. As we will see, there are also other approaches like contextual bandits and reinforcement learning, but in this talk I'm going to focus only on bandits. So bandits take their names from where you are in a casino and you are facing all these different slot machines, and your goal is that you want to make as more money as possible. You don't actually know in the beginning which slot machine will give you more money. So what you want to do is that in the beginning you want to explore a little bit in order to find out how much money every machine gives you. And then once you figure out that this is the best machine, you want to exploit the benefits from this machine. So you want to keep pulling these slots. So this is the way that bandits, this is the main way that bandits try to work, is that they're trying to balance this exploration exploitation trade-off that everyone faces in every interactive system. So to be more concrete, what bandits assume is that there is this agent who is selecting different actions based on some policy, and then there is the environment which is giving the context. So the context, for example, could be the user features and so on. And also the environment gives reward on the action that the agent chose. So what is important is that the environment gives reward only on the actions that the agent chose. So that is the concept of bounded information, meaning that you don't have full information. You don't know what reward you would get had you chosen a different action. So that's exactly why there is this exploration exploitation trade-off. And now the goal of the agent is that he wants to maximize the cumulative reward of the different actions that he chooses. Now, the different policies for bandits that we can see in this slide are the following. So one is epsilon greedy. So epsilon greedy is that with a probability 1 minus epsilon, the agent is going to choose the action that has the maximum estimated reward. And with probability epsilon, it chooses a random action. And so that's the way that the exploration part is happening. However, in epsilon greedy, you actually have to tune what this epsilon parameter should be. Now, an alternative bounded policy, which balances the exploration exploitation trade-off, is the UCB algorithm, upper confidence bound. So in this algorithm, what the agent chooses as an action is the action that has the maximum sum of two terms. So the one is again the estimated reward of the action, and the other term is some term that shows how confident the agent is that this action is the best. And you can see that this term actually becomes smaller the more times you are playing this action. So this is the n sub t alpha term. Okay, and now the third policy is the policy of Thompson sampling. So Thompson sampling is actually a pretty old approach. However, it became really popular recently because it gives really good empirical results. So Thompson sampling, what it does is that for every action, it samples from the posterior distribution of what is the posterior distribution of the reward for the action. And then it picks the action which has the largest sample. And so given the fact that the agent has chosen this action, it gets the feedback, and then given this feedback, it updates the posterior distribution. And as I mentioned, there are also these other contextual bandits and reinforcement learning, but we're not going to focus on that. Okay, so before I move on to the use case of having interactive learning for recommendation in terms of restaurant recommendation, I just want to tell you that interactive learning is prevalent across different domains. And so essentially in every domain that there is this interaction between some sort of an agent and some sort of an environment. And in any domain where you want to understand what would have happened had you chosen something else, and you're trying to balance this exploration exploitation trade-off, interactive learning can actually be used. So that could be in the domain of medical treatments, in the domain of website optimization, or in all different controlled experiments like A/B test experiments, or for example in personalized assistants which are conversing with their user, and of course in recommendation systems that we're going to focus for the rest of this talk. This slide is just for reference for those of you who are interested in more details about bandits for recommendation. The work that I'm going to talk about is, of course, not the only one on bandits for recommendation. So, for example, Lean UCB is a very popular contextual bandit algorithm for news recommendation. So I would encourage any of you who is interested to look more into these links. Okay, so now we're ready to talk about the use case, which is the use case of conversational recommenders for the domain of restaurant recommendation. So this is based on work that we did with Philip Redlinsky and Katja Hoffman, and this is published in KDD 16 for those of you who are interested in reading the paper. So the main motivation of this work is that, let's say you are in a new city and you want to decide where you want to eat dinner tonight. So the problem is that there are too many options for where to have dinner, and you don't know anyone around the city and you don't know anything about the city. However, if you ask the local, then probably what he would do is that he would first ask you a couple of questions, like, do you like seafood or do you have a car? And this question would probably be contextual in the form of, if, for example, there are really good restaurants around the corner, then the do you have a car question doesn't have any meaning. So, and then after this couple of questions, he will be able to give you a good enough recommendation. Similarly, in this work, what we argue is that instead of asking a local, you could be asking a human-like recommender, meaning you could go to some app in your phone and you could converse with it. So this app could be asking you a couple of questions. So you say, could you give me a recommendation for where to have dinner tonight? And then it asks you, sure, how hungry are you? And you say, not very hungry. And then it asks you, do you prefer Chinese or Indian today? And you say, I prefer Chinese. And then it gives you a recommendation. So anytime you want to design a conversational recommender, there are two questions you should be asking yourself. So the one is, what do you want to ask to the user? And the second is, how do you want to ask this question to the user? So I'm going to describe now what are the key building blocks that we use in order to address these two questions in this work. So the first one is that you need to have some implicit structure among the items and the users in order to be able to efficiently propagate the feedback that you get on a given user and a given item among the different items. And so for that, we need to have a model. And as you will see, the model is going to be a latent factor model. Also, exactly because we have this exploration exploitation trade-off, meaning that you are a new user in the system. So this is essentially you've never come to the system before, and that's the cold start problem. You have to face this exploration exploitation trade-off. So we need to have this explore exploit strategy to probe the space of the items and to allow for continuous learning. And finally, you need to have some feedback elicitation mechanism, which is a mechanism that tries to get the user's feedback. And for this work, we selected either absolute or relative feedback. Okay, so the big picture of our interactive recommendation pipeline is actually really similar to this interactive learning for recommendation slide that I showed you before. As you can see, again, there is this part of the model and there is this part of the user. But what is important here is that the user is a cold start user, meaning that the system has never seen this person before. So, okay, so the steps of our pipeline is that first we pick a model, which will be the latent factor model, and we also pick a preference elicitation mechanism. And then using some offline data of how different users have interacted with different restaurants, we initialize the model. Then the mechanism selects a question to ask the user, and the user answers the question. And then using this feedback of how the user answered the question, all the model parameters are updated. And then you remove this question from the set of allowed questions. Then the mechanism selects the next question, the user gives feedback, and so on. And after very few questions, the model can present to the user its recommendations. Okay, so now I'll go to more detail about every building block of this whole pipeline. So the first is, what is the model? So the reason why we need the latent factor model is because we need to have this principled way of selecting questions. Because imagine again, if you were asking a local and he would be verbally asking you a few questions, then these questions wouldn't be random about different restaurants, but he would have some principled way of asking these questions. And so this principled way will actually come from our latent factor model. And this is exactly the model that I talked about in the beginning of the talk. So this is the probabilistic mass factorization model. However, if you remember, this model assumes feedback of the form like or dislike, click or no click. But in reality, many people are actually better at giving pairwise comparisons instead of absolute judgments, meaning that they're better at saying, I prefer this restaurant over that restaurant, instead of saying, I absolutely love this restaurant or I absolutely hate this restaurant. So for that, we actually modify a little bit the latent factor model. So we have for every user I and every item J, you have this noisy affinity that we saw before. However, you similarly have that for user I and item H. And so taking the difference between the two, you have this variable now, noisy affinity difference, which tells us how likely user I is to prefer item J over item H. Okay, so this was the model building block. Now, the second step is that we need to initialize from offline data our model. So we use some logged observations in order to do that, and we learn the offline embedding, meaning we learn all the variables of the biases, the traits for both users and items. And then for every item, we initialize its prior distribution to be the corresponding posterior distribution for the traits and the biases correspondingly. Now, a new user comes and he's a cold start user, so we know nothing about him. So we can assume that this user is actually the average user. So we can assume that his prior distribution, this comes from the average of the posterior distribution of all offline users, both for the traits and for the biases. So this is where we place this cluster user in the embedding. Now, the third building block is that we need to have some way of selecting questions to this specific user. And so the strategies that we're using are strategies that are inspired from the bandit learning literature. And these are the algorithms that we actually talked about before in the beginning of the talk. Also the active learning literature, and we also have some baselines. So for bandit learning, you can see here the upper confidence bound. So if you remember the upper confidence bound, the agent there, he picks this action that has the maximum possible reward estimate plus some confidence bound. So here the reward estimate, it comes from the mean of the noisy affinity distribution, and the confidence bound terms, it comes from the variance of this distribution. Similarly, for Thompson sampling, we maintain this posterior distribution across all different items. You have the noisy affinity distribution for this given clustered user and all possible items. So you sample from every possible sets distribution and you show the item which has the maximum sampled noisy affinity. Now for active learning, the idea is a little bit different. So instead of trying to balance the exploration-exploitation trade-off, what active learning does is that it tries to maximize information gain. So two different strategies that you can see here is that one, you can show the item that you are the least confident about so that you can reduce your variance about that. So you show the item which has the highest noisy affinity variance. Alternatively, you can show the item that contains the most information. So for example, you can show the item that has the highest L2 norm of the trait vector. And you can also see that there are these exploit only or explore only baselines. And now using one of those strategies, you now decide to show to the user this restaurant, like, do you like Cafe Siciliana? And you get the feedback from the user to be, let's say, no. So then you get this observation of this user, this restaurant, 0. So then this observation is used to update online all the parameters of the model. So you can see that the noisy affinity distribution of this specific user and item is changing. So the mean shifts and also the variance shrinks. But this happens not only for this specific item that was in the question, but also for the nearby items in the trait embedding. So, and that's exactly the way that we can efficiently propagate the feedback among the items. So far I have actually described to you all the pieces that you need if you wanted to ask absolute questions. However, what if you want to ask relative questions of the form, do you prefer restaurant A over restaurant B? So for restaurant A, let's say you assume to do Thompson sampling, you will just do exactly as you did before. Let's say you show the item that has the maximum sampled noisy affinity. However, for restaurant B, you actually want to show a restaurant that is kind of relatively apart in the latent embedding from restaurant A, because you want to have some way of quickly cutting down the space of the questions. So in order to do that, what we do is the following construction. We assume that we have this virtual observation that this user, this restaurant A, 0, that he didn't like that. And then we update the posterior distribution, and then we set this prior to be this virtual prior to be the posterior distribution after incorporating this virtual observation. And now using this virtual prior, you can pick item B, and actually this is going to be really far apart in the latent embedding because of this construction. So now let's say that the user preferred the Cafe Siciliano in the restaurant A over restaurant B. So now how do you translate this observation back into the model so that you can incorporate that back into the model? So because here at the beginning we use this absolute model, meaning the probabilistic matricization, which assumes observations of the form like or dislike. One way you can incorporate that is by saying that, okay, the preferred item is actually like, whereas, so that's the abs pos method. Whereas in the abs pos negative method, what we do is that we assume that the preferred item is a like, whereas the less preferred item is a dislike. Alternative, what you can do is that you can interact with the pairwise model. So for restaurant B, you can just show the item that is the most likely to be preferred compared to restaurant A, meaning that it has the maximum noisy affinity difference from restaurant A. And then you incorporate this observation back to the model. Now, some insights that we got from this work is that I don't have the time to actually show you the different results that we have, but one is that best performance can be achieved with absolute questions. Second is that even if you have relative feedback, all three of our methods can actually have effective learning. Another is that just by doing this offline embedding at the beginning to warm start the model can actually greatly boost the performance. And we also saw that bandit-inspired question selection strategies are very effective. However, the most important insight from this work is that we have envisioned these recommender systems that can converse with new users to learn their preferences. So now, before I conclude this talk, I actually want to give you a little bit of an insight to another work called Collaborative Ranking with a Push at the Top. So this was work with my advisor in AIWTB 2015. And the reason why I want to mention this work is because so far what I assumed is that if we return back to the domain of news recommendation, I assumed that the model actually gives only, it shows just one news article to the user, and then the user gives feedback on that. However, in reality, what happens is that the model gives us ranked list of news articles, and then the user considers this ranked list top-down, and then it gives feedback on that. So the main key ideas that this work was based on is that first, recommendations should be treated as a ranking problem instead of a rating prediction problem. And what I mean by that is that, for example, in Netflix challenge, the whole goal was to just predict that this movie is 5 stars, whereas this movie is 3 stars, and so on. However, in reality, what you want to do is that you want to make sure, instead of predicting the right number of stars, you want to predict that the movie with the more stars is going to be ranked higher than the movie with less stars. Second, you don't actually need to rank all possible items properly, but you do want to have the very top of the list to be ranked properly, because this is exactly what the user is actually going to consider. And third, there is this analogy between recommendation systems and learning to rank. So the analogy is that in learning to rank, you have a query, let's say Florence, and you have all possible documents or URLs which are pertinent to the query, and the goal is to be able to rank these documents for the specific query. Similarly, in recommendation systems, the user is the query, and you're trying to rank all possible candidate items for this specific user. So exactly because there is this analogy between learning to rank and recommendation systems, in this work we were actually able to borrow this novel idea from the learning to rank literature, which is this construction of ranking with a push, and this is work by Cynthia Rudin. So we translated that into the setting of recommendation systems. So first of all, imagine that you have just a single user, and somehow you are given this score of how, for this given user, you're going to score the different items. And so this is the F sub I score. Now, if you sort all these possible items based on this score, you can have this ranked list, and now you can actually check the ground truth and see which one of those items are positive or negative examples for the user, meaning likes or dislikes. And now for every possible dislike, you can count how many are the number of likes which are below it. So this is a number, and this is what we're calling height. And so this is the number that you want to have small, because you don't want to have positive examples underneath negative examples. And you also want to penalize larger heights, because this corresponds to negative examples closer to the top of the list. And the way you penalize that is by placing this convex increasing function on top of the height. So the more steep this function is, the higher you penalize these negative examples towards the top of the list. However, in the previous slide, we assume that this F sub I score is given to us somehow, and we assume that we have only a single user. However, in the domain of recommendation, we have multiple users, and we have this idea of collaborative filtering. And so the score is a score actually given by our recommendation system. And so you can model this score to be the inner product between the two latent traits of the user and the item. So plotting this in the construction of the height and also replacing the 0-1 loss with the logistic loss, you can actually have this surrogate height. And then if you also place this convex increasing function on top of the height and you sum all over the users, then this is objective that you have to minimize. So you see here that, for example, the height, the push objective that we put here is the P norm. And so the higher the P, the more you penalize the negative examples towards the top. And you can see here that this objective is only a function of the latent traits U and V. And so we actually update those parameters using stochastic gradient descent. And the main insights that we get from this work is that first, it actually makes sense to treat recommendation as a ranking problem. As you can see here, actually we have more experiments in different data sets, movie data sets, and so on. However, you can see this only for movie lengths 1 million. that compared to just probabilistic methodization, all our methods give a big boost in performance. And also we can see that just by comparing that to having a separate ranking function per user, having this collaborative component helps a lot. And of course, there are other works treating recommendation as a top ranking problem. However, you can check these links here. I'm not going to talk about those. And I just want to mention that this whole work, that this last part was actually based on offline recommendation. However, there is ongoing work of trying to translate that into the interactive learning for recommendation setup. So now to conclude, first of all, I hope you can see that if you link bandit learning along with recommendation systems, for example, collaborative filtering techniques, this can open up exciting possibilities for interactive recommenders that can converse with their users. We actually showcased that we have this effective use of interactive learning for the case study of having the conversational recommender for the domain of restaurant recommendation for cold store users who are new in a new city and trying to find where they should have dinner tonight. And finally, we saw that treating recommendation as a top collaborative ranking problem helps a lot. So with that, I conclude. Thank you so much for watching this talk. And I'm now going to move towards the chat. Okay. So right now I don't see any questions. I'll be waiting for you guys for a bit. Thank you so much. Very nice comment. Sure. Okay. So one question is that if I have a link for the research, so I can probably just put here my website in the chat box. Thank you so much, guys. You're really nice. Perfect. Okay. So one question is that how long does it take to move from the average user, the cold store user, to actually giving good personalized recommendations? And what will this take? So let me move then to the presentation again. Okay. So for example, you can see here that for this context of having absolute questions, which is this gray line, you can see that just with 2 questions, you're able to get from 0.6% of average precision in top 10 to around 0.75. So that you can get a very good performance. However, you can see that the more questions you are asking, the better it is. And you can get, let's say, after 11 questions, pretty good performance around 1. Of course, 11 questions is something that is a lot. So the whole idea there is that you wouldn't be asking this many questions in a single interaction session to the specific user. But what will probably happen is that this could actually be this whole interactive learning scenario of you go into the app, it asks you a couple of questions, and then if you go to the app again and it will ask you another few questions, then it would probably continue to move this user embedding as well. However, we can see that just with a few questions, like 6 questions and so on, you get pretty good performance. I hope that answers the questions of Eleni, but let me know if you want more clarification. Right, so another question is that what is the difference between active learning and bandit learning? So let me move to that slide. So the main difference between active learning and bandit learning is that bandit learning makes this assumption that you're trying to balance this exploration exploitation trade-off, meaning that you don't know at the beginning which action is going to give you the most reward. So you need to explore a little bit by trying all different actions. And then once you figure out that this is the best action, you want to reap the benefits. So you want to exploit that. So this is the main assumption that bandit learning makes, and that's why it's so ideal for interactive learning, because generally speaking, in interactive learning, there is this exploration exploitation trade-off going on. Now, active learning, what it does is that it tries to actually, at every question, it tries to gain the most information possible. So let's say it would be asking about the item that it is the least confident about. So just by asking about this item, let's say that has the maximum variance, you are going to get the feedback of the user on this specific item. So you're going to reduce your variance about this specific item, but also about the items which are close in the embedding. So that is going to allow you to, by reducing the variance, you're going to get more information about what the user actually likes or dislikes. Or for example, you're going to be showing the item that contains the most information about the user. So that would be, for example, an item that has the maximum L2 norm for this trait. So this is the key difference between bandit learning and active learning. So both are really good approaches. It's just that bandit learning is actually both approaches, they are suited for interactive learning. It's just that bandit learning is balancing the exploration exploitation trade-off, where active learning is trying to maximize the information gain or to do variance reduction. Awesome. Okay, so one question is that can both be combined in a system? I guess the question is about whether both active learning and bandit learning can be combined for the system. However, let me know back if there was a different question. So, okay, that was the question. So I guess these are two different strategies for, let's say, for the domain of restaurant recommendation. These are two different strategies of trying to ask the different questions to the user. So, for example, we have this slide here that I just want to share with you. I'm not sure if I had much time to do that before. So let me just find the slide. So you can see here, for example, that we tested for the absolute questions, we tested both bandit strategies and active learning strategies. So bandit strategies here are the Thompson sampling and UCB. And similarly, the active learning strategies, these are the maximum trait magnitude. The other, the maximum variance, had actually really similar performance, so I don't show it here. So you can see that actually both of those are performing really well. However, if you turn to the domain of trying to ask a relative question, you can actually see here that Thompson sampling is pretty good and also UCB. Whereas if you turn to the maximum trait magnitude, you can see that it's not performing that well. It's not learning that fast as the bandit learning strategies do. Okay. So Lenny told me that we can't actually see the slide, but let me show it to you again. So this was for the relative questions. This you can see with the green line, this is Thompson sampling. Whereas you can see with the blue line, this is maximum trait magnitude. So this is for the relative questions. So you can see that actually bandit learning is doing better in the domain of relative questions for restaurant recommendation. However, to answer the question, I'm not aware of a way of combining both bandit learning and active learning together in some strategy. However, you can be comparing the two. Although there could be some work combining the two, I'm not sure actually. So now another person is asking me, what are your thoughts on using deep reinforcement learning? So as I told you, interactive learning can actually happen not only with bandits, but actually with reinforcement learning. So the main idea is that reinforcement learning is much more general compared to bandits, because if you remember, in bandits we have this agent and we have the environment, and the two are interacting, and so the agent is learning based on multiple interactions with the environment. However, the assumption that bandits make is that whatever the agent takes as an action, it actually doesn't affect the state of the environment. However, in reality, let's say you have this conversation recommender where you want to keep the state of the conversation, for example, the state of the user. This could be changing over time. So if you wanted to do that, actually reinforcement learning is a very good approach to do that. Now, regarding deep reinforcement learning, meaning that combining deep neural nets with reinforcement learning for that. So the deep learning component, this would actually come if instead of trying to engineer specific features, let's say for the user or for the restaurants, you would have the deep learning to actually try to infer these high level or fine-grained features. So in this work, actually, we found that the latent features that are learned for the user and for the items in the question, they're actually really valuable. So they can really quickly help us to have these good recommendations. However, I can imagine that maybe you can gain higher boosts in the performance of, let's say, how good the recommendations you're able to give after a few questions. Maybe using deep learning you can get better performance. So lately, with all these deep learning advance, actually deep learning has been coming to recommendations as well. So I don't remember an exact paper, but I think in Pandora or Spotify, and recently also in the Rexis conference, were people which were using deep learning for recommendation. However, I don't think that for the interactive recommendation part, this has happened yet. So that's an open possibility. Right, so the question here is that, so is bandit learning basically reinforcement learning with a certain set of assumptions? I think it's fair to assume that bandit learning is a sub-case of reinforcement learning. So, and the key assumption is the one I mentioned before, and it's that instead of having the agent taking actions that affect the state of the environment, you don't assume that this happens. And so, for example, if you are in this setting where, let's say, you have this user and you're trying to ask some questions to the user so that you give him a good recommendation. If this is a cold store user, you can assume that this is a user that is that comes IID from the distribution of users. So whatever you are asking to him, it actually doesn't affect the other users. So there isn't this effect of trying to change the state of the environment. So that's why in this work we chose for bandit learning. However, if you want to keep track of the state of the environment, then reinforcement learning is much more general. Let me see if we have other questions. Perfect. So I think that was it. Thank you so much, guys, for watching the presentation. And thank you so much for your questions. If you have any other question, you can definitely ask me in the chat and I will be responding to you. Let's see if we have some last minute questions, else like in 2 minutes I will finish. Okay, so thank you so much, guys. Goodbye. Oh, just the last question that I got from Babak. So the question is that if I can show the slide for the recommendations for how to do further reading on the subject. So let me just share that with you. So these are the other works on bandits for recommendation. So a really cool approach is Lean UCB. So this is in the domain of contextual bandits, and this happened in WWW 2010. So basically, they augment the UCB algorithm with linear regression. And of course, there is a lot of work by Deepak Agrawal, and this was work in ICDM 2009. This is Explore Exploit Schemes for Web Content Optimization, and they have actually been doing more work in this domain. Also, there is this cool work by Zhang et al. In SICM 2014 called Interactive Collaborative Filtering, and they use a similar collaborative filtering model. It's just that they don't update the latent traits of the items, they just update the latent trait of the user. Also, there is work by Jaya, who I'm really happy that she watched this talk as well. So her talk is NIPS 2015, Efficient Thompson Sampling for Online Message Authorization Recommendation. And they were using particle filtering in order to update the different variables in the probabilistic method authorization model. So these are the main works. And now, if you're also interested in how you can do collaborative ranking, then there are these works, Coffee Rank, which they're trying to optimize the convex upper bound of NDCG, which is some metric that captures top ranking, and this is the 2008 work. And there is also the work by Yushi and al., which is in Rexis 2012 that got the best paper, and they're trying to optimize some smooth lower bound of the mean reciprocal rank. And of course, there is ongoing work in ranking bandits. So these are the main works. And also I want to mention that another work in interactive bandits, a lot of people like John Langford has actually been doing a lot of work in interactive learning. Oh, let me just make sure that the slide is visible. So this is the one. Oops. This is the one. I can definitely send you a screenshot of the slide in the chat as well if you want. So this is the one part, and then this is the work on recommendation as ranking. This is the coffee rank, and this is the CLIMF. Okay. Awesome. Great. So if there are no more questions, thank you so much for listening. It was great to present to you the work, and have a great rest of the day.